Alright, so this is the second lecture of supervised machine, nonlinear kernel tricks and the practical guide. So before we move on, so this is what we're going to cover about SVM. And we already covered history, large margin definition, and the margin definition, and the optimization formulation. Is this too light? Too bright, right? Yes, all right, so this is better. So history, margin definition, and the optimization formulation. So today, what I'm going to cover actually is the last two sections in this whole different elements of SVM. SVM is extremely complicated and mathematical derived model. So I split it into three different sections. So this is the nutshell of SVM. When last time we covered half of the basic optimization formulation, but not exactly this formulation on here. Today I'm going to, actually next time I will cover how do the C got introduced in this optimization formulation. So today it's really about representation. So how do you represent samples? So the most important idea behind SVM is called kernel trick. And that kernel trick is the definition actually just a inner product. It's really, so instead of thinking about each sample represented by features, now I'm thinking about similarities among two samples. The majority, the most important features, the most important pattern make use in the SVM is not raw features, it's pairwise similarities among samples. And how do you produce it? It's produced by something called kernel trick. So for example, in this case, kernel behind sample X and sample Z is its phi X, which we learned before, its basis expansion of the feature. Inner product is the phi Z, which is the basic expansion of the point Z. So this still sounds pretty hard and abstract, and we're going to introduce why this is. I see, so there's actually a small mistake here. So the curve, I'm going to fix it, should supposed to be X and Z. So but it can be Xi and Xj, and then you replace Xi and Xj here. So most important is we're using pairwise similarities as the major features, major important pattern to use for classification. So last time we talked about classifying using linearly separable SVM, and then so the linearly separable SVM, it's really simple, right? So for example, you're given the training data, like in this case, so you have only one X, only just one X, which is a number line. The colors represent the different two different groups, two different classes. And really easy, what you're looking for is the separation margin, left and right, which we call X minus, X0, and X plus, right? This is how we defined in the last class. Then the margin, the distance among X plus and X minus is the margin. That M margin equals to actual 2 over W. And that's what we proved, W transpose W. So maximize margin equivalent to minimize W. Then subject to, you classify all the samples correctly. So this side is -1, this side is +1, -1, +1, and then subject to, if you still remember, for all these points in the training data, I want to have my yi, which is the true label, times the xi or maybe W transpose I. It's the same thing, W transpose xi plus b larger or equivalent to 1. So this whole thing is the formulation. The whole thing is the scoring function to train W, to look for the W and the B best fit my training data, which is represented by the point here. So this is what we covered last time, right? So this sounds really nice. However, when you have square root, yes, you're right. Actually, yes, this has a square root here. Yes, thank you. Yeah. So this sounds nice, right? But however, when you look at the data, just there's a little bit error or some kind of noise. Like this red point is on the right of the two blue points, and there's no way you use a linear separation to separate the points, the 2 points here. So what can you do? Very easy. So same trick as we did before. Regression goes to polynomial regression, and you just add a new feature space. You convert your x space into phi x. So our old is x, right? It has olding feature x. Now I'm just converted it into phi x, including both x and x squared. And in this space, you actually can find, you can totally just use a linear separation line to separate the two classes. And this is exactly the trick. So in this case, this is called sec. Don't worry about this red point I just added there. So now we moved from the left case called the linearly separable case into this is called non-linearly separable case. We can totally separate two classes using actually it's equivalent to a nonlinear line in the original space, but actually it's linear line in the phi x space. So this is almost the same trick we had before. Extend linear regression into polynomial regression just by extend x into phi x. So even more complicated, but actually very there are a lot of data looking like this. So you might have some kind of one class quite densely together, and then the other class all like distributed almost all over the space. And how would you separate this? So there's no way in the original space, x1, x2 space, you separate the two classes, the red versus the blue, using a linear separable hyperplane, right? We actually define hyperplane. However, if you just extend the x into phi x, then you actually can separate the two different classes, red versus the blue, just by adding one more feature is the x1 times x2, and then also use x1 quadratic, x2 quadratic as the representation. Then you can find a linear hyperplane to totally separate the two cases, the two classes. Okay, question about this.
How did you find that equation?
Good question. So in the end, what do you even know phi x, right? Which phi x? It's coming in the future slides. All right, so just to summarize, when you're given a feature mapping phi, we define the kernel K as Kxz, which equivalent to phi x transposition phi z, and then we actually in the kernel SVM, and I do not need specifically no phi. The only thing I need to define is actually K. instead of defining the phi, what I need to define is k. So this sounds still pretty hard to understand, but you will be getting clear in the future. So for this one, it's very simple. So this is one type of kernel. It's 2x1, x2, x1 quadratic, x2 quadratic. This is the first type phi1, right? This is more like a polynomial kernel. And you can also use, this is called Gaussian or RBF kernel. And to do the separation of this type of middle is dense and the other class is almost surrounding to separate the two. So the whole idea is I'm looking for nonlinear separability. I'm using a kernel mapping phi, and then in that kernel mapped space is linearly separable. And it's equivalent to I'm learning a nonlinear boundary function in the original X space. So this remarks is a little bit linear device. So the whole thing is when we see that we use the kernel trick, it's very important for SVM is when we see that we use the kernel trick to compare the cost function using the kernel. So don't worry, we're going to talk about later to compute. We mean we actually do not need to know the explicit mapping phi. What we really need to have is just this function. So like this function, I don't know what phi, but it's equivalent to phi x transpose phi z for a specific phi. Maybe phi I, let me just try this phi 2. And the previous design is phi 1, right? So in this design, I have this specific phi, but that's just, I know. But in fact, when you use in SVM, you don't need to know phi. You just need to know what to define the k. So it will go getting very clear in the later slides. So okay, all right. So a little bit theorem. So why do I want to map to the higher dimensional space? Let's look at the when there are 3 points in your training data. When you have 3 points in your training data, you can separate it in R2 space. You can always separate 2 training points or 3 training points with whatever classification combination, a 2-class combination it has. You can always use a linear line to separate the 2 cases. Question about this, because this is the key. It's the fundamental idea of SVM. So, for example, this is the first combination. 1 is white, 2 are yellow. You can always find a separation line, right? And the other case is a 2 white, 1 red. This is the case 3 white. This is the case 3 red. And then this is the other case also, it's this dimension. So whatever combination for the 3 points in terms of their labels provided by training data, you can always separate it, linearly separate it into 2 classes. Question about this? And this is just called linearly separable case. We can always linearly separate them to 2 classes when you have 3 training points. All right, then we extend it. When you have endpoints, in general, you can always linearly separate them into 2 classes in the n-1 space. So in the end, it just shows me if I can project my feature x into a phi x, if I have n data, I can project it into n-1 or even larger larger than n-1 space, then in that phi x space, I can always linearly separate the two classes. If it's larger or equivalent than n-1, it's guaranteed I can find a linear separable hyperplane, given the n training data. That's the reason why we like to project it into higher dimensional space, because we can always separate them into two classes, no matter what are this original permutation of the class labels for that endpoints. Sure.
Aren't we increasing the complexity of the model? I mean, we are...
Great question. So if you go to the phi x, then what's the computational cost? That's exactly the question we're going to answer. And why? That's the reason why the kernel trick. All right. So, we go to x to phi x and already had it. So there's a reason why you do x to phi x, because you want to project into higher dimensional space, make your training data to be able to be separated, linearly separated. +1 class and -1 class. All right. So the next thing we're going to talk about is, but how do this phi x even related to the SVM optimization, right? My SVM optimization is minimize the margin subject to every point is predicted correctly. There's nothing really about that phi at all, right? Or how do you use the kernel? You told me, you don't need to have explicit phi x, you only need the k. But how do you use the k in the optimization, in the training, and use the testing? So this is actually very complicated. It's related to the representation, related to the scoring of SVM formulation. It's also related to what do we mean models for SVM. So next class, I'm going to talk about this much more clearly. So today is just a quick intro. How do the kernel even related to the training objective function? So this is the review. What we had is minimizing the W transpose W, subject to all the training points are predicted correctly, and then it's summarizing into really just summation of all the elements take square of the W, and then subject to that formulation we had. So this is the objective function, right? If I want to change x to phi x, it looks like the only strategy I can use is to replace the x here into phi, right? Because that's the only place x is even used. Since the only strategy is to change xi to phi xi. This is the training because I want to optimize to get W and B, right? That's my stage of training to fit the parameters. However, the SVM uses something called dual representation of that quadratic programming. Instead of encoding the classification rules, and we're going to use something called walk-ranging multiplier, and to encode those correct classification constraints as part of object optimization formulation. So let's go back to see. So this is my objective function, or maybe it's still equivalent to 1/2 W transpose W. So I maximize the margin. At the same time, to require my parameter make sure all the training labels, all the training points are predicted correctly. So this Lagrangian multiplier, so if you learned about numerical optimization, this is a very generic trick. I converted the constraint into part of the scoring function. So I converted my objective function as, again, 1/2 W transpose W. This is the same way, yeah, it's a little bit different from our way, but let me. And a minus something called alpha I. Alpha I is the Lagrangian multiplier. I have a total of, let's go back to this formulation we said. How many constraints do we have? We have n trained data, then we have n constraints. For each constraint, I'm using a weight function, a weight scalar, trying to weight that constraint by adding it into the objective function. So for each constraint, I create a parameter called alpha I, and then multiply yi times, this is the prediction function. So I want this together to be larger or equivalent to 1, right? So this together larger or equivalent to 1 minus the 1. So it should be positive. And all the alpha I, it's what you pick. It's actually, it's called Lagrangian multiplier. They should all larger or equal to 0. So what can you tell me? What is this? I have a non-negative weight combining all the constraints and then make them part of the scoring function. If this smaller than 1, what it gives me, if this part, well, any of our training data, this part, instead of larger than 1, is actually violating my requirement to be smaller than 1. Then this part is minus. When this part is minus, this is positive numbers, right? Positive values. This part is what? This is positive, and this is what? This is the whole scoring function I'm trying to. So let's go back to, I'm trying to minimize, right? I'm trying to minimize this part. I'm trying to minimize the W transpose W. At the same time, minimize this, right? Because I'm pushing this to be positive. If this is negative, this is not minimized. So this is a weighted summation of my margin goal and my classification goal together into one shared scoring function. Questions about this? If you learned about numerical optimization, you should, learn this in the basic form. How do you add constraints into the scoring function? Sure.
So why is alpha different for like different samples?
Good question. In this case, because they are different constraints. There are totally n different constraints. They are not the same constraint. So you have to have different weights to show how much that trade-off contributing into the scoring function. And this is actually a parameter to learn. So there are a lot of things actually to be sure.
If the YWTX plus B value is greater than 1, then that whole part starts going, that goes positive, so
Yeah,
again,
then this is
contributes to
negative.
minimization.
This is because there's a minus here, and this is negative. This is good, right?
So,
But
so
if
that,
this is smaller than 1,
yeah, so that contributes to minimization when it's satisfied value.
Yeah.
Can you over satisfy? Can you essentially create a model that's so warped at certain points that it doesn't produce the best model but produces the minimization there?
so if I can paraphrase what your question is, You mean this is too large?
Yeah, so essentially when it's
Oh, I see. This is dominating over this, right? Good question. So this is the basic form. We haven't talked about there actually a parameter here called C that controls how much you care about misclassification versus how much you care about the margin. That's exactly that C parameter controls. And this is which is next class. And this is just the basic form because there are already so many more you added there. All right?
So will not the alpha control the same thing? I mean, if it is very large and alpha will be so small that it will.
Yes, but there's a global parameter too. There's a global parameter actually controls how much you care the summation of the misclassification versus the margin. Yeah, that's the next class because there are too many concepts introduced once, so I'm introduce one at a time. This time it's the alpha called the Lagrangian multiplier or alpha sub I. It had so for every training data, there's alpha I. Every training sample. All right, this is so complicated, right? It's even more complicated. It's something you have to derive because besides the W and B parameter, now you also need to look for alpha parameter. So now you need to look for W and B best fit the data. At the same time, also the alpha sub I control that balance of my data point, my current data points misclassification contributes to the whole misclassification. How did they penalize? This is a huge, there's so many parameters. And then there are a lot of ways to do this. You convert this summation, this summarized new weighted summation, consider both the constraint and the object, the margin objective function, and you try to, don't worry about all the steps, but if you can read it, but if you cannot, in the end, you can convert the formulation into not about W and B at all. It's only about alpha. And this is called a dual form. And actually, it's if you have some kind of numerical optimization background, it's not that hard. You try to, in the end, it's the whole idea still is that loss function versus the W to be 0. Hopefully, this is the best W. That loss function versus the B to get the gradient set it to 0, it gets the B. So these two formula converted into W can be reformulated into a formulation related only to alpha, yi, and xi. Alpha I, yi, and xi, and also the same thing you can derive. B can be derived through analytic equations related to alpha, x, and y. And then you substitute the W and the B into the loss function, the whole loss function, and this is a new objective function you get. And this is actually the basic SVM loss, the scoring function. It's a little complicated, I understand it, and then, so look at this, right? And this is my revised formulation, and instead of minimize, my older goal is to minimize in versus WB, right? Now I maximize, and there's a reason why I maximize. I'm going to talk about it next time. So just memorizing for now. So now I'm trying to maximize this newly formulated dual form of objective function, at the same time satisfies constraints actually required through the W and B derivation. First of all the alpha I need to larger or equivalent to 0, and summation alpha I, yi equals to 0. And this is actually a very, very strong constraint, which gives very good properties to SVM training and testing. And because of this formulation, so now let's see this formulation. What is it? So this revised formulation is I'm trying to maximize in terms of the alpha now. So there are actually n, alpha 1, alpha 2, until alpha n, alpha 1, alpha 2, until alpha n, different parameters. I'm trying to learn to fit my training data. And then the whole formulation revised into this. So instead of using the phi or x, I only need to use xi transposition xj. What I only need the dot product among all the samples to learn the alpha. And then this is the training, right? During the training, I get all the alpha. So after I have all the alpha, I use the analytical form I derived. W equals summation alpha I, y xi, and then just substitute the W into, how do you do performance and how do we predict? Our prediction is fx equals to sine function W transpose x plus b, right? And for maybe a x test. Very simple. You substitute the W into here. What you get is summation of all the alpha I, that yi xi, then transposition the specific test samples, which is exactly here. Question about this? This is called the do form for linearly separable SVM. And this is the reason why kernel trick works, because we really do not need to have original phi. What we need is just x transpose x, and then if we extend it to phi, what we really need is just k xi and x test, which equivalent to phi xi transposition phi xts. So I'm extending this linear form into nonlinear form. All right, so you might be confused by here. So because I want to introduce next time. Because a very good property of this formulation, what we get, the majority of the alpha are 0. Most alpha I actually is 0. Only the support vectors, which is your margin that to boundary touches on, those points has alpha I larger than 0. There's a good reason why this is good. So because during the testing phase, this is a summation sigma alpha I over yi, then this x, the inner product formulation. If the alpha I is 0, you don't need to calculate it at all. What you need to calculate is only that kernel or this inner product values of your test sample versus the support vectors. Question about this. This is one of the good reasons SVM, the dual formulation is better than the original formulation. All right. Okay, so now we extend it from linear to nonlinear, from x to phi x. So if you think about it, what you feed in this is the training, right? That you need to feed into your training, and So in the original X case, equivalent to, you are creating a similarity matrix. The similarity matrix includes all the training data versus the other training samples, and each element is xi transposition xj. When you have this linear extension, what you're performing is a similarity matrix. Each entry is phi transposition xi times the phi xj. So this is what you, in the end, the training data provides is this matrix to this formulation, because I really do not need original phi at all. What I need is that similarity among xi and xj. It's in the form of inner product. So this is still a little bit confusing. Why does reformulation even matter, right? It's coming in the next few slides. All right, so I hope you understand from the linear to nonlinear, it's extremely simple, but just converting that x transposition xj into phi xi xj and then replace it into kernel xi and xj. And then in the, sure.
Just small question. Why was the alpha not 0 for these bounded cases and 0 for all the rest?
Oh, you mean in the training?
Yeah.
Because in the training, you don't know. You are learning the alpha through the training. You do not know which one is 0, which one is not 0. But this is actually a very good property. All this state-of-the-art optimization method makes use of the sparse pattern of alpha I to look for alpha I very quickly. This algorithm, almost all the state-of-the-art packages use something called SMO. It's exactly using this most alpha are 0 properties in the design of searching the alpha who is not 0. So you can start from everything is 0. Start from every alpha is 0. You look for those non-zeros, which is a much simple case when you start from random. Then look for who is 0. So there are a lot of tricks people use to train the SVM quickly by considering this extremely sparse pattern. SMO, actually check it out, it's a very beautifully designed algorithmic design making use of the sparse property of alpha I. All right, so this is the test case, and what you need to get is this vector of your test sample versus the training sample. But actually what you need is only the support vectors, your test sample versus the support vectors, the kernel value or the inner product values. So, sorry, there's some kind of, this is all phi. So, so why do I care about there's no phi? So there's some reasons behind is SVM is a very good tool to solve two issues simultaneously. It uses the kernel trick for efficient computation. I'm going to talk about why it's efficient. And also the dual form assigns the parameters only to the training samples, but not to the features. I'm not assigning weights to the features, I'm assigning sample the weights, the learnable parameter, actually each assigned to the samples, training samples. So what is kernel trick? Why is it even efficient? The whole idea is you never represent phi. You just directly calculate k, x, and z. There are very good theorems behind something called reproducing kernel Hilbert space idea, which I'm not going to cover here. Feel free to read why this is good. And more concretely is, this is the normal kernel we normally use. Instead of define phi, we directly calculate polynomial kernels like this. So this is our polynomial kernel calculation in SVM. Instead of decomposing x into x1 quadratic or onto x1 polynomial p, forget it. I'm only doing an inner product x and z plus 1, then together take quadratic d. Why is this good? Why is this good? Instead of having this explicit each xi onto polynomial d, and then doing inner product phi x and transpose phi z, I'm just directly design the polynomial kernel, polynomial similarity as 1 plus x transposition z, and then together power of d. Why is this good? Why is this good? Yes, it's easy first, then second. Why is this good? Why is this representation good? It's an efficiency, right? Why? Think from the efficiency perspective. How many flops, how many performance computation you need if you do this? It's OP. It's an OP computation from this for performance, right? But if you decompose it, actually to explicitly write it into all the possible polynomial terms, what will be the O for this? This is OP to the D. So this basic form is only OP cost. But if you do this explicit phi x, phi z, that all the polynomial representation, then doing the inner product, this is actually cost OP to the D power. And actually you can prove this equivalent to one of this. So this is what we mean, the kernel trick is an efficient way to extend into phi x representation. And there's another one much more interesting called RBF kernel, which is this form. In fact, this is extremely simple, right? It's also OP. Okay, so what is this cost? X minus z, element-wise minus, then take the length, quadratic, which is a computation cost of, it's still OP. There's no quadratic, whatever, at all. So this is still an OP cost. However, this kernel equivalent to, in fact, phi x is infinite size. You can't even write it's an infinite, you can actually prove it. So I'm not including that proof. Feel free to, there are actually a lot of, I can put you extra reading material about why this equivalent to phi x is infinite size. So, why infinite size is good? Why infinite size of the nonlinear space I projected to is good for SVM? We just talked about it, right? Why it's good? Come on, we just learned about it. VC dimension. Whenever you have a finite size of training data, n data points, you can always linearly separate it into in the n-1 space. And this actually goes to infinite size of space, which means what? You can always, actually this kernel is a very generic kernel. You can always separate the two into your data into two cases because VC dimension is guaranteed. Question about this? And there's a reason why you like this kernel. And also, of course, it's computationally efficient. There's only OP cost.
So
Sure.
will this work with the lesser number of data, because in previous regressions or so we require n to be greater than p. and here P is greater than N, that is number of samples.
Oh, you mean high dimensional case?
Yeah.
Can you rephrase the question again?
I'm just asking that in previous this regressions and so on, so we require N to be greater than P, right?
Oh, you mean, yeah, just to paraphrase the question is, in the linear regression, we want to have, because the inverse, right, that's really because of the rank of that matrix X transposition X. If you want to have the inverse, the rank should be full rank. So you have to, the P larger than case guarantees that matrix cannot be inverted. In this case, no, it's not relevant. So that type of theorem, P versus N, it's a different, so we can use that type of derivation here because it's not about rank, at least for now. So this actually needs a very, very totally different type of analysis to prove what's the minimum of N. Which I'm not going to cover here. And there's a reading material about, that's more like asymptotic behavior. How many N are necessary for me to help me learn a good classifier? All right, so we don't specifically compute it implicitly because the computational efficiency and also because for some kernels you can't even have the phi-x explicit at all. So now let me give you very concrete cases about this 1 plus x quadratic z, the polynomial kernel. In fact, the polynomial kernel matches to the phi-x, have all the elements like this, 1, x1 term, linear term, and quadratic term, pairwise interaction term, until actually really, really long. And you can prove it for the polynomial 2 case. So in this case, we have 2 features. We have, let's just prove how do you get it. You can decompose your phi-x into 1, x1 term, linear term, quadratic term, and then interaction term. And this is the x phi-x, this is the phi z, and then you do phi-x transpose phi z, you can get exactly this equivalent to 1 plus x1 z1 plus x2 z2 quadratic, which is this transposition phi-x, which is exactly this, and they equivalent to each other. But in fact, what you truly did derivation is 1 plus x1 z1 plus x2 z2. This is only cause OP, which is 2 computation, right? So I'm actually because that the one plus it's a constant computation. It's not increases with the number of features. So that's why I'm saying this cost is OP. I hope you understand what I'm trying to say here. Because plus 1 is a constant cost operation. And also quadratic is also a constant cost operation. So that's why I don't have OP plus 2 here. And this is a big O definition, hopefully you still remember from the algorithm class. And this cost is OP quadratic. It's very easy to see, right? 1, 2, 3, 4, 5. Yeah. It's actually, there's a constant before the P. Yeah, so in fact, there's a constant before the P quadratic, but because the big O, so I got that constant in the multiplication out, and also the plus the constant operation out too. Because plus 1 is the constant operation. Yeah, I hope you, okay? So this is very basic asymptotic analysis. All right, so in the end, to optimize in SVM, this is my SVM basic form operation, right? Observation. What I need to have is that matrix, right? the whole matrix has all this training sample versus all the other training samples, it's related to this matrix I draw right here. So this element is OP cost in the linear case. And I need to calculate all the pairwise kernel. So to calculate this matrix, what's my computational cost? Because yeah, they're n squared, and also it's because the inner product guarantees what? When you have an inner product, it guarantees symmetric, right? So we actually talked about this many times before. That's I transposition xj equals to xj transpose xi. And this matrix is symmetric. So which makes the computation in the linear case is OP times n quadratic over 2, but because it's constant, you can actually cancel, don't show it. And in the nonlinear case, for most of the kernel we use, each this k, xi, xj costs also OP, which is the same as the linear case, OP times n quadratic over 2. So you can tell what? In SVM, when you use this kernel trick, computationally, you really don't add much. But it's extended to very nonlinear space by not requiring much of the extra computation. You already performed in your homework 2, you have to extend it using that nonlinear extension function. Whenever you have the power d, you extend it from the p to the p power d, and that specific formulation will induce p power of d times n quadratic total cost. But the kernel trick guarantees you have only just OP times n quadratic, of course over 2, I cancel that 2 out, computation cost. Question about this? Alright, so you might feel weird. So I don't just write alpha I larger or equivalent to 0 in a lot of formulations. In fact, this C larger than all the alpha I is exactly the next class if it's not completely separable. Because you want to allow a little bit noise in the margin region. The whole formulation, if you allow a little bit noise, the whole difference is only in that C part. So this is the third reason why the dual form is such a nice form from the original form, and which we're going to cover next time. Alright, just to summarize, with the original form, this is my observation. With the kernel trick, the only thing revised is from X transposition transpose Xg into K. That's the only thing differ, and it's the same computational cost. But it gives you a much better guarantee, right? Because the VC dimension, this theorem of SVM, VC dimension just guaranteed in this larger infinite phi-x space, you got better separation boundary to be able to search. It's easier to search for the linear boundaries in the phi-x space. The VC dimension guarantees you actually can solve this better when your phi-x is larger. Alright, so this is the testing case. So yeah, I already talked about it. You can prove it why this is equivalent to infinite phi size. So I'm going to skip this to the next time, skip a few slides because I thought I can finish it. Because I want to talk about the practical guide. It's for your homework. So just a little side detour. We already talked about the whole thing you need is KXZ, right? is that similarity matrix, and which really extend SVM from the numerical type of X. So in a lot of cases, you don't even have X, right? So assuming you have when X numerical X is even not available, it's just not making sense. So it's pretty difficult to represent maybe like a graph, sequences, or all those symbolic type of data. You don't have a numerical representation. It's very difficult to come a numerical representation, but it's extremely simple to come out a similarity measure among graphs, among strings, among maybe those symbolic structures. And SVM doesn't require you to use X. It only needs the K. So this opens a whole paradigm of the potential applications of SVM, right? If you can design KXC, because it only requires these pairwise similarities. As long as you can define who is more similar to the other. And then you can use SVM to perform principled classification. And this is really important property because I do not need to convert it into numerical X. What I need is only similarities among samples, which is for each different domain, that type of similarity is normally pretty easy. If two sequences are similar, I can use equidistance, right? I don't even need to have a representation of X, of sequence into numerical. I can use Hamming distance. I can use whatever making sense for my domain. I only need this. So which is extremely important properties that helps SVM to be applied to many real-world applications. All right, so I have 5 minutes left. I really want to go over something called a practical guide. So I have a lot of things, but next time I'm going to cover this. So what you're going to use is something toolbox called libSVM. And there's some other software called SVM Lite or SVM Torch, but until now, libSVM is the dominating toolboxes people use. And based on all my derivation, you can also tell it's kind of difficult to implement SVM because there are so many things behind. It's not a simple algorithm. So for this homework, we're using the toolboxes. So the steps for using SVM in homework is prepare the feature data matrix, select the kernel functions, select the parameter of the C, which I haven't even told you what's the C, but it's one of the important parameters. Without knowing, you can actually just directly try to code, but I'm going to talk about on Wednesday. That C parameter controls how much you think about the misclassification's importance in the final scoring function versus the margin contribution in the final scoring function. So very important is the data format. I think maybe you already know about it. So actually Panda already hide all the details behind. So maybe this is not very critical, but again, so most SVM toolboxes require the data to be formatted in this specific form. This is actually some form called sparse representation. You can actually tell in this column, I don't have the feature 3 because it's 0. I don't need to represent it. So this is a pretty good form when your feature are sparse. A majority of your the features are 0. You don't need to represent all the zeros using, all the rest until the resolution you like. You can just represent this into a sparse form, which is a very good format to save disk, save memory. This is called, another computational concern, right? We want to have efficient, not in terms of only speed, but also in terms of memory and disk cost. Alright, so the other thing is, how do you represent categorical features in this SVM? Honestly, you can design kernels, but in our homework, I feel that's actually too much. So we just use some simple strategy to convert categorical features into called basis vector based representation, which I think you already had. Have they worked on the encoding? No, not. So in the end, just if you have discrete features have three different possibilities, you're going to use a vector with size 3. If it's red, it's 0, 0, 1. Only one of the entries is 1, and so all the other entries are 0. So this is called basis vector-based representation to represent categorical features. The other important feature, extremely important, it's actually not just for SVM, it's also for deep learning or the other, it's the scaling of your feature. So there are different ways to scale your feature. So we actually talk about in the k-nearest neighbor case, right? If one feature's range is so large, like a weight versus height, and the weight is normally, if you use the whatever kilogram of, they're always a much larger number compared to the height. Height number is normally within, if you use inch, it's normally like within the 6 and 0, but the weight is normally like 0 to 300, maybe 200, yeah. So it's very difficult if you do not normalize your features. The weight feature will dominating over the height feature. So especially if your data are small, and it's very tricky in those cases. So that's why you want to either normalize data or scale data. There are different strategies. Normalization normally pushes all the features into 0 mean and variance 1, or the scaling just push the features to be to be bounded from 0 to 1. And this is the classic equation to scale your data. And there are many different ways. Actually, feel free to read how to do centering only, which means pushes the mean to 0 but doesn't care about variance. Or you also do normalization, you push the mean to 0, variance to 1. Or you only use scaling through those kind of linear conversion, like scale it into 0, 1. Yeah, but also very, very important is don't touch your test samples. When you're trying to calculate what is the max, what is the mean, okay, you have to have the max, mean, or the average to do the centering, right? Don't touch your test data. That's a good practice, just to let you know. Because you should not touch the test data, unless that's a semi-supervised setting. And in the SVM, it's very important to remember, you need to use those scale parameters you use in the training to apply those parameters on the test data. You should not learn a new set of scaling parameter on your test data, then apply on the test. That will be totally destroyed your data. Yeah, it's already 15:18, so and missing values, I mean, you just do frequent value submission, or you use the mean value. There are a lot of tricks. There are also out of dictionary tokens. So if it's a categorical variable, there may be, it's just not in your dictionary, which I meant your training data has 4, maybe 3 cases, but in your test data, there's one extra symbol in that feature never happened in your training data, which means your training library doesn't even know what is it. And this is also a classic case called out of vocabulary issues. And this is very classic for natural language processing because in there they have a lot of rare words or new words. There's just no way your dictionary cover all the possible words. So I think that's, yeah. So then next is model selection I'm going to cover next time. In the end, be careful when you're doing the feature processing of your SVM homework. out of vocabulary, missing values, centering on scaling data, and also categorical feature presentation. And that's it. Thank you.